Last class, we did Newton's first law of inertia. Basically, we did all three types of inertia: inertia of rest, inertia of motion, inertia of direction. Then after inertia, we did momentum, which is the product of mass and velocity of the body. The next is Newton's second. Newton's second. So according to Newton's second law, the external force acting on the body is, its statement says that external force acting on the body is directly proportional to rate of change of momentum. This is external force, which is directly proportional to rate of change of momentum. So you can write this as that the external force which is acting on the body. So see, what is rate of change of momentum? Let at time t1, the momentum of the body is t1. At some time instant t2, momentum of the body is t2. So in time interval delta t, in time interval delta t, where delta t is basically t2 minus t. Change in momentum is delta p, which is t2 minus p. So the rate of change of momentum. Sania, what do you mean by rate of change of momentum? What do you mean by rate of change particularly? Yes. Rate of change means? Remember, rate of change means change with respect to time. Whenever a quantity change with respect to time, that is rate of change of momentum. So rate of change of momentum means change in momentum with respect to time, means change in momentum over time. Newton's second law says that if you apply a force on the body, external force on the body, external force F external is directly proportional to rate of change of momentum. This is Newton's second law, that external force acting on the body is proportional to rate of change of its momentum. If you remove the sign of proportionality, you will get that F external is K delta P over delta P. In all system of unit, this K is equal to 1. Whether you take SI unit, CGS unit or any other unit, this K comes out to be 1. In all units, this K is equal to 1. So you can write this as F external is change in momentum over time interval. So this is the external force acting on the body, which is change in momentum over time. This is the external force acting. Okay, so what type of force is this? Is it an average force or instantaneous force? Can you decide?
I think average.
It's average. Whenever you have delta in your equation, this is average, Sania. Whenever you have delta in your equations, the quantity is average. For instantaneous, okay, now tell me, what will you do for instantaneous force? Fazil. A very to move from average to instantaneous. What's that step?
Derivative.
No. Yeah, derivative. But to go for derivative, there is one intermediate step. And that says take limit delta t tends to 0. It's delta p over delta t, which is dp over dt. So if external is dp over dt. So this is the external force acting on the body, which is rate of change of momentum, d over dt of t. This is instantaneous. So whenever you have average, you will have delta in your equations, but once you have instantaneous, it's d, means you are differentiating momentum with respect to time. Okay, just note it down, then we'll move further. This is Newton's second law, that force is rate of change of momentum. So in this expression, F external is d over dt of p, dt over d. How much is p? What is p here? How much is p?
Momentum.
Momentum. And the formula for momentum?
mv.
So instead of p, I can substitute mv. If I substitute mv, then your F external will comes out to be its d over dt of mv. So here m is constant. You can take this m out of this derivative. So you are left with F external is m dv over dt. And this dv over dt is acceleration. This dv over dt is a, acceleration. So you can write that this F external is mass into acceleration. So Newton's second law, for a system having constant mass, if I'm saying that mass is constant, then it reduced to this simple form, that force is mass multiplied by acceleration. But for system having variable mass, So Sania, can you suggest me a system having a constant mass? Any example of a system which have a constant mass? Give me a real life example of system having constant mass. Like you can take a car, force acting on a car, the car have a constant mass. You can take a truck, this truck have a constant mass. You can take this pen as a system. The mass of pen does not change. The majority of the system that you encounter is a system having constant mass. Tell me another example of system having variable mass. Can you name a system where mass varies, a system having a variable mass? Okay, if I take the case of rocket. Rocket is a system having variable mass. The majority of mass of rocket is that of its fuel. As a rocket moves, its fuel burn out. Means the major mass of the rocket is that of the fuel. As fuel burns, the mass of rocket decreases. So rocket is an example of variable mass. You can take one more example. If you take a balloon, the mass in a balloon, the major mass in a balloon is that of air. If you allow the air to move out of the balloon, then the mass of the balloon keeps on decreasing. So if you have a system variable mass, example, if I take a rocket, in that case, F external is d over dt of mv. I'm repeating the calculation from this step. Because over this step, I use the term that mass is constant, then I take this m outside, I integrate, differentiate velocity. Now, if I'm saying that mass is variable, so can I take this mass outside?
No.
Can I take this mass outside of this differentiation?
No.
No. Because we can't take variable thing outside. We can only take constant thing outside. Can I take V outside? Velocity? Yes. Can I take V outside? Yes or no? No. Obviously,
No.
body is moving, its velocity is changing. If you apply force on a body, then its velocity will change. So you can neither take this M outside nor this V outside. So you have to differentiate both MV. So differentiate both M and V, you have to use product rule. Product rule says keep one quantity as constant, differentiate another. So I assume M to be constant and differentiate velocity. Then this rule says, okay, now you have taken M as constant, now take V as constant and differentiate it. This is the product rule basically. If your mass is variable, then you can neither take your M outside nor your V outside. So you have to differentiate both simultaneously. So differentiate two terms simultaneously. The rule says first assume any one of the term as constant. So I assume M to be constant and differentiate it V. Then take another term. Like first of all, I differentiate V and I take V outside and differentiate it. This is the expression of for a system having variable parts. This is force for a system having variable mass. If a system have constant mass, then this is the expression of force F equal to M. Sania, is it clear?
Yes, sir.
Equation 1 and this equation 2. Okay, now tell me, can I apply this expression for a rocket? So rocket is a system having a constant mass or a variable mass?
Variable mass.
And this equation is valid for?
Constant.
So can I apply it for rocket?
No.
No. For rocket, you will use this equation. But can I apply this equation for a truck?
Yes.
On the highway? Yes, you can apply.
Yes.
So that's the difference between these two equations. This equation is valid only for a system having a constant mass, but this you can apply for a system having a variable. So that's it. Now, force is a vector.
Sir?
Yes, Father?
Sir, in the second one you have written like V into dm by dt. Then how are we gonna calculate dm by dt?
dm by dt is rate of change of mass. If in a question it is given that 3 kg of rocket, the fuel burns in a rocket in 2 minutes, then dm by dt is 3 by 2 seconds. Is the rate at which mass changes. So here dm by dt is rate at which mass changes.
Okay.
It's rate at which mass changes. That's dm by dt. Okay, the next is force is a vector. It's a vector quantity. Its SI unit is Newton. CGS unit is dyne. One Newton is 10 raised to the power of 5. That's the relation between Newton and dyne. 1 Newton is 10 raised to the power of 5. Okay, let's study some more units of force. Okay, if you measure your weight on a weighing machine, or if you buy some food stuff from the market, then what is written there? Weight. Let's say you buy a packet of 1 kg from the market. Then at the back of the packet, the weight is written as 1 kg weight. This is how the values are written. Have you seen it? 1 kg weight, 2 kg weight.
Yes.
What is this? This is mass or weight?
Weight.
If you buy anything from the market, at the end there is written how much is its weight basically. It's 1 kg weight, 2 kg weight, 3 kg weight. What is this? This is weight or mass?
Mass.
Remember, SI unit of mass is kg. Weight is a force. SI unit of force is Newton. So if 2 kg weight is written, what does it mean? It's mass or it's weight? Okay, no idea. See, if I take a any measuring instrument, like if I take a beam balance or anything, a weighing machine always measure weight of the body. It never measure mass of the body. You always measure, whenever you measure something, it's mass, it's basically weight of the body. So ideally, that weight should be in Newton. If you buy something from the market and at the back it's written 2 kg weight, this doesn't mean it's the mass. Kg doesn't mean mass, it means it's weight, it's force. But instead of Newton, that force is given in terms of kg weight. So I'm repeating it again. The unit of mass is kg. The SI unit of force is Newton. But if you measure something from a weighing machine, then that weighing machine never measure in Newton. That weighing machine measure in another unit which is known as kg weight. So it's a very common misconception that you think that kg weight means you are measuring mass. You're not measuring mass, you're measuring weight. So what happened there is you have two types of units of force. Two types of unit of force. One is absolute unit. Another is gravitational unit. There are two types of unit of force, absolute and gravitational. This gravitational is basically a practical unit that we use. The best example of practical unit is, what is the SI unit of energy? What is the SI unit of energy?
Joule.
Joule. But if you buy any food stuff, then the energy is written in joule or in calorie?
Calorie.
Calorie. So that calorie is which unit? It's not the SI unit. It's basically the practical unit of energy. So there is a difference between the SI unit and practical unit. In terms of energy, the practical unit is calorie, not the joule. Similarly, in the case of force, the SI unit is Newton, but we never use SI unit. We usually, in day-to-day life, we use practical unit, which is kg weight. So this is absolute unit. You have two types of absolute units. Or you can divide your absolute unit into SI and CGS. The SI absolute unit is Newton. The CGS absolute unit is dyne. The relation between Newton and dyne is this: 1 Newton is 10 raised to the power 5. When you come to gravitational unit, then again you have two types of unit, SI and CGS. The SI is kg weight. The CGS is gram weight. That's the difference between kg weight and gram weight. SI is kg weight, CGS is gram weight. 1 kg weight is 9.8 Newton. So when you see any packet of 1 kg weight, that means in terms of Newton, that is 9.8 Newton. 1 gram weight is basically 980 dyne. So your weighing machine measure weight, which is a force, but that weighing machine does not measure in Newton. That weighing machine measure in kg weight. So if the reading of a weighing machine is 60 kg weight, that means in Newton that is around 600. Is it clear, these two units?
Yes, sir.
In most of the calculations, we will always use absolute unit. But remember, in some calculations, maybe gravitational unit is given. So if it is given that weight of a body is 2 kg weight, then to convert that weight in Newton, it's multiplied with 9.8. Okay, solve this numerical. $300K. Okay, solve this question. So you have initial speed of scooter, which is 36 km per hour. It comes to rest means final is 0. Time taken is 5 seconds. First calculate acceleration. You can consider this as uniformly accelerated motion. Initial velocity is 36 km per hour. So 36 into 1000 by 3600. Or you can multiply it with what? 5 by 18. So that's 10 meter per second. It comes to rest, that means final velocity is 0. The time taken is 5 seconds. So, okay. Acceleration is, you can use this equation. V is u plus a. So V is 0, u is 10, a is not given, t is 5. Sanya, why is it 6 point something? Minus 10 by 5. You didn't convert this in meter per second?
No.
Why not? This is kilometer per hour. You have to convert this in meter per second.
Yeah.
So this is acceleration minus 2 meter per second square. Now you can easily calculate force, which is the product of mass and acceleration. So the mass of the body is 300 kg. Acceleration is minus 2. So the force is minus of 600. Minus sign just tells that the direction of force is opposite to that of motion of force. The significance of negative sign. Negative sign tells the direction of force and acceleration are exactly opposite. A bullet of mass 0.04 kg hint for this numerical is you can use this expression v square minus u square is 2s. And Sanya, this time take care of units.
Sir, we will take 0.
This is initial. Yes, if it stops, then means final velocity is 0. V you will take 0. You can easily use this equation v square minus u square is 2s. Your v is 0. Your u is 90 meter per second. Your displacement is 60 centimeter, which is basically 0.6 meter. Put all values here. Then this is 0 square minus 90 square is 2 into acceleration into 0.6. So minus 8100 is 1.28. So your acceleration is minus 8100 by 1. It comes out to be minus 6750 meter per second. Now if I calculate force, then force is mass into acceleration. So your force is mass is 0.04 kg. multiplied by acceleration, which is 6750. So the force here comes out to be, this acceleration is negative, minus of 270. Next question is, a rocket so see, if you have a rocket, this is at rest on the ground and mass of the rocket is m, let's say, which is given as 20 kg. So the initial blast that is given to the rocket is for two purposes. That initial blast serves two purposes. The first purpose is that initial blast accelerate the rocket. It gives an acceleration a to the rocket, which is as mass into 5 meter per second square. That initial blast also helps in overcoming gravity. Like its weight is acting down, you need some force to overcome that gravity, and that's mg. So the initial blast, initial thrust of blast is equal to thrust for acceleration a, thrust for acceleration a, plus thrust to overcome gravity, thrust to overcome gravity. So initial thrust of blast is, thrust for acceleration means force required to provide a acceleration, that is ma, plus force required to overcome gravity. To overcome gravity, you need a force mg. So the initial thrust of the blast is ma plus mg. I'm repeating it again. There is a rocket which is at rest on the surface of Earth. You need a force to provide this rocket with an acceleration a, and you also need force to overcome the gravity, because gravity will not allow this rocket to move upwards. So the force that you, thrust is basically force, nothing else. Thrust is a force which is acting perpendicularly. So applying force to provide acceleration a to the rocket, and also to overcome gravity. Overcome gravity means mg. So applying a thrust or a force which is ma plus mg. Is it clear? Noor, Rania, you both have not missed any significant part of the theory. You just have missed some numericals. You just have missed this expression that force is mass into acceleration. That's it. Nothing else. So this is the initial thrust that you are providing. So you can write this m a plus g. So force is m is 20 kg. A is acceleration, which is 5. G is acceleration due to gravity, which is 10. So that's 20 into 15. So that is 3,000. No, not 3,000. 300. Just note it down. This is a NCRT problem. Let's erase it and move on to next one. So the next topic here is impulse. Not impulse, it's Newton's third law. After Newton's second law, it's Newton's third law. Here Newton's third law says to every action there is equal and opposite reaction. Newton's third law says to every action there is equal and opposite reaction. So to every action, there is equal and opposite reaction. That's Newton's third law. That means if I take a system having two objects, pen and my hand, if pen applies some force over my hand and I call this as action, then at the same time, this hand will apply a force on the pen in opposite direction. That's reaction. Action and reaction are exactly equal in magnitude, but they act in opposite direction. Means if action is acting along positive x-axis, then reaction will act in negative x-axis. For example, if I give you two objects, I call this as object A and let's call this as object B. You have two objects A and B. They are placed in contact. You can say both hands are, this is A and this object is B. This is object A, this one is object B. Object A will exert some force over B. So this is the force on object B by object A. So this is the force on object B by A. Similarly, object B will exert some force over A. This is force on object A by object B. You can call any of the force as action, then another one will be reaction. If you call this as action, then this is reaction. You can even say this FAB is action and your FBA would be your reaction. So these are action and reaction pairs. Newton's third law says that action and reaction are equal and opposite. Equal and opposite means they have exactly equal magnitudes, but they act in opposite direction. So if action is acting to the right hand side, so the reaction will act to the left hand side. Few more examples. There are some features of action and reaction. The first one is action and reaction are instantaneous. These action and reaction pairs are instantaneous. Means at the instant the action happens, at exactly the same instant you will have reaction. There is no time lag. It's not like if this pen apply force over my hand at some time t equal to 0, then after 5 seconds my hand will apply the force over the pen. There is no time lag. The moment this pen apply force over the hand, at the same moment this hand will apply the force over the pen. So action and reactions are instantaneous. Okay, tell me one more thing. These action and reactions act on two different bodies or on the same body?
Different bodies.
Different bodies.
You jump, the action is over the floor. The reaction is over you. So action and reaction always acts on two different bodies. Acts on two different bodies. Hence, they don't cancel each other. So this action and reaction acts on two different bodies, so they just don't cancel each other. So this is one marker question. Why action and reaction does not cancel each other if they are equal and opposite? They don't cancel each other because they're acting on two different bodies. They're not acting on the same body. Then there is one exception to this rule. There is only one force in mechanics which does not have reaction. There's only one force. That is known as pseudo force. Pseudo force does not have reaction. That is the only exception to this rule, Newton's third law. Otherwise, each and every force in nature have its reaction except this pseudo force. We will do pseudo force in details, but not now. After Newton's third law, the next topic is impulse. So this impulse starts from the concept of impulsive force. To understand impulse, you first have to understand what is impulsive force. Impulsive forces are those forces which act for a very short duration of time, and they have significant effect on the system. The time for which the impulsive forces act on the system is very small, but they have a significant effect on the system. Few examples, like if like the case of a bat and a ball. When bat applies force on the ball, the time of contact is very small. Bat and ball are in contact for a very short duration. It's even less than 1 second. But the force that bat apply on the force during that short duration is very large. The effect of that force is very large. But the time of contact for which the force act is very small. You can take one more example, like you can take the example of a nail. If you have a nail, you strike this nail with a hammer. If you strike this nail with a hammer, then the time for which hammer and nail are in actual contact is very small. But that have a very large effect on the nail. This nail goes deep inside the box or wherever you put this in. So impulsive forces are simply forces which act for a very short duration of time. So forces which act for a very short duration of time are known as impulsive. Example, force on nail by hammer. It's an example of impulsive force. Force on ball by bat is an example of impulsive force. So these are a few examples of simple. Even if someone slaps, this is again an example of impulsive force. The time of contact is very small. If I draw a graph of impulsive force, I take time and I take force. Here, initially your force is zero, its force is zero. The moment the impulsive force start acting, it increases. And then finally, it decreases to zero. This is what happened in case of hammer. Before the hammer strikes the nail, the force is zero. The moment this hammer strikes the nail, force increase from zero to maximum value. And again, when you remove this hammer, the force again reduced to zero. So the time of contact, this particular time of contact is very small. This is the impulsive force. Is it clear, the concept of impulsive force?
Yes, yes, clear.
Yes, sir.
Yes, sir.
So when you have impulsive force, then you measure the total effect of impulsive force. The total effect of impulsive force is known as impulse. So you can write impulse is the total effect of of a large force which acts for a short duration of time. To produce finite change in momentum. So it is the product of average force and time of contact. Basically, the impulses is represented by I. So this is the average force that is acting on the body. So here in this case, okay, just tell me, this force is a constant force or a variable force? What this graph tells, is it a constant force or a variable one?
Variable force.
The variable force, because initially your force is 0, then it becomes maximum, and then it becomes 0 again. So it's a maximum force. It's a variable force. We take average of this variable force and multiply it with the time of contact. Delta T is the time interval for which both the bodies were in contact. Delta T is time of contact. Next, what you can do is you can write your average force in terms of momentum. If I use Newton's second law, using Newton's second law, I can write that average force here is change in momentum by time interval. This is Newton's second law basically. You can write Newton's second law in two ways. You can either write this force as mass into acceleration. This is Newton's second law. You can even write Newton's second law in this way, that average force is delta P by delta T. You can just substitute 2 in 1. Substitute 2 in 1 and get the value of I. Substitute equation number 2 in 1 and get the value of I. Get the value of impulse. So if I substitute 2 in 1, then your impulse comes out to be its average force, which is change in momentum over time multiplied by time interval, gets cancelled out. So impulse comes out to be change in momentum. Your change in momentum is final momentum minus initial. This is your impulse, which is equal to change in momentum, which is final momentum minus initial. Impulse is a vector quantity. Its SI unit is its force into time. So SI unit is Newton seconds. It's a vector quantity. So the SI unit is force multiplied by time. So the SI unit is Newton seconds. So you can, in numericals, you can use any of the relation. You can either use average force into time, or you can use change in momentum, means final minus initial momentum. In majority of questions, this will be an easy approach. You will have sufficient data to calculate velocity. But to calculate this force in time, there are very few numericals where you have data to calculate force as well as time. In majority of numerical, you have data to calculate change in momentum. Let's start with this question. So this is a wall. This is the ball. Okay, Rania, tell me one thing. Is velocity of ball same before and after striking, colliding with the ball?
Remain same.
It will remain same. No. Velocity is a vector. It depends upon direction. So, Rania, if the ball is going rightwards, what's the direction of velocity? Positive x-axis. So, Rania, what is the direction of velocity after collision? It's again along positive x-axis, now along negative x-axis. Rania.
Negative.
Negative. So, direction is same or it gets reversed?
Reverse.
So, if direction gets reversed, that means velocity changes. Remember, velocity is a vector. Direction is equally important. When it says that speed is same, that means magnitude of velocity is not changing, but direction is changing. Is it clear now? So for impulse, I can use this simple expression. This is final momentum minus initial. Final momentum minus initial momentum. Okay, just see and tell me whether this problem is one-dimensional or two-dimensional. It's a one-dimensional problem. Say, initially ball is moving along x-axis, right? So it's a one-dimensional problem. Initially ball is moving along x-axis. Even after the collision, ball is moving along x-axis. So it's a one-dimensional problem. It's a 1D problem. So one dimension. So in 1D problem, you can replace this vector sign with just sign convention. It's P final minus P initial. So you can write your P final as mass into final velocity, mass into initial velocity. You can take mass as common. This will be final velocity minus initial velocity. Next, you can write your initial velocity Vi as V. This V is the initial velocity, so Vi is V. Your final velocity V final. If I consider this direction as positive, then this has to be negative. So if I call that my V initial is V, then how much is V final? It will remain V. How much would be
minus
V?
V. Minus.
Minus V. So if I substitute the values, it's M. V final is minus V. V initial is V. So impulse is M. It's minus of 2V. So impulse is minus of 2mv. So that is your impulse. This is the impulse imparted on the ball. Just by looking at this negative sign, Sania, can you predict the direction of impulse? Which one?
Positive.
Positive. See, I consider right hand side to
Yeah,
be
negative. Negative. Because it's going.
right hand side is positive. It's positive x-axis. It's negative.
Yeah. Sorry.
Direction of impulse is negative x-axis. Okay, can you guess the type of collision? If the speed is not changing, is it elastic or inelastic collision?
Elastic.
Elastic.
Yes, elastic. If it were inelastic, then speed should have decreased. If speed is not decreasing, that means your collision is elastic. Just like that. Do one more question. Now this is the wall. This is ball, it strikes the wall and then it rebounds. Let's see again, this is a one-dimensional problem again. Impulse is final momentum minus initial momentum. But the here problem is again one dimension, so you can just remove the vector sign P5 minus P initial. So it's mv final minus mv initial. I can take m as common. This is v final minus v initial. V initial is 10 meter per second. V final is minus 8 meter per second, because if I'm taking upwards to be positive, then downwards is negative. And the mass of the body is 5 kg. If I substitute all these values here, it's 5. V final, which is minus 8, it's minus 10. So 5 into minus 18, it comes out to be minus 19 Newton seconds. Let's do one more question. Now this question would be two-dimensional. Like if this is a sword example of NCRT, this is a wall. So this ball is moving in this way, it strikes the wall, and then it rebounds in this way. This is mass m. It's moving with a velocity v. It's mass m. It rebounds with the same velocity. Let's call this angle as theta. This is again. Okay, now, so this is a two-dimensional problem. So ball, strike a wall. Okay, so if this ball of mass m moving with the velocity strikes the wall and then move in this way, it's very clear that during motion of the ball, both x as well as y axis will change. So to solve these type of problem, the best thing is just resolve your velocity along x and y axis. This is your initial and this is your final. Just resolve your initial and final velocity. If this is theta, then this is theta again. This velocity will have component. It's along x-axis, it's v cos theta. Along y-axis, it's v sin theta. You can even resolve your final velocity. This will be v cos theta, and this is v sin theta. This is v cos theta and v sin. So this is your initial and this is final. So the resolution simply means I divide this velocity along x and y axis. So I divide this problem along x and y axis. So we'll solve x axis separately and y axis separately. So along x axis, Rania, what is the initial velocity along x axis? How much is ux? Ux, I call this as initial. Ux initial is v cos theta. I'm considering right hand side as positive, and for y axis upwards is positive. Rania, keep telling me some basic things. How much is ui, initial velocity along y axis? Rania, let's try, even if you are wrong, let's try. This is your initial velocity. I resolve this along v cos theta and v sin theta. How much is ui initial?
V sin theta.
It should be positive or negative, bache? It's positive or negative?
Negative.
It's negative. Okay. Very good. Let's do final velocity. X component of final velocity. Rania, keep telling. How much is Vxy? Not Vx initial.
V sin theta.
Vx initial, Vx, X, not Y. V sin theta is along Y axis. Along X axis is V cos theta. So if I'm taking right hand side to be positive, then this will be negative, minus of V. Okay, Rania, the last thing. How much is Vy final? Y component of final velocity. How much is Vy final?
V sin theta.
It would be plus or minus?
Plus.
plus. See, this is going upwards or downwards?
Negative.
It's downwards, no? So it should be negative. Now, let's calculate impulse along x-axis. If I calculate impulse along x-axis, then along x-axis, your impulse is final minus initial along x-axis. So that's mass into final velocity along x-axis minus mass into initial velocity along x-axis. Then you can take this m as common. This is final velocity along x-axis minus initial velocity along x-axis. You can write this as this is m. How much is final velocity along x-axis? That's minus v cos theta. Initial velocity along x-axis is minus. This is initial velocity along x-axis. Let's call this as v. V x initial, v y initial. So this is initial and this is final. So minus v cos theta minus v cos theta. So Ix comes out to be minus 2mv cos theta. That's Ix. Similarly, we can calculate Iy. It's P final along y-axis, P final initial along y-axis. Just you have to check this will comes out to be 0 because initial and final velocities along y-axis is 0. It comes out to be 0.